Hi everyone, Eric again. Came to talk about Gauss's law. This is the second part of this series. Might be a three-parter, might be a two-parter. I don't know. But today we're going to talk about more stuff that has to do with Gauss's law, um, because it is kind of a complex topic. So I'm going to again attempt to clarify some of the parts of Gauss's law. So this is Gauss's law, integral enclosed of the electric field with respect to all the tiny pieces of area is equal to your charge enclosed divided by permittivity of free space epsilon naught, or again, epsilon naught is a constant. And the most interesting part of Gauss's law is figuring out what this Q enclosed is. If we can do that, the rest of it is relatively straightforward. I will make that more clear as we go forward. So something else I wanted to introduce were these variables called charge densities. There are three different charge densities that you might end up seeing. And the definition of charge density is kind of, it's in the words. So it's how densely packed your charges are, right? So if you have an area and you put one charge, the charge density sigma is going to be 1 divided by the area of your space, and that's kind of like mass density, how regular density is mass divided by volume, because you want to know how much mass is contained in a certain amount of volume. So same idea with charge density, where this rho here is going to be the charge sigma the charge volume density, which is going to be equal to the charge divided by the volume. And then this last one is going to be the line charge density. So if you have a line of charges and you want to know how close together they are on that line, you take the amount of charge divided by the length of the line. These will be important moving forward when solving the Gauss's law equations, because oftentimes you are given a sphere that is packed with charges. So you have charges distributed uniformly along this sphere. And the problem will just give you what's called a charge density. So it'll tell you that the charge density rho is equal to something. Like, let's say I was trying to find a number. But let's just call it a number, right? The charge density is some number. We then could solve for how much this sphere, how much charge total this sphere is holding if we know the radius of this sphere. So if we know the radius of the sphere, r, we can figure, and we know this charge density, which is some number, we can figure out how much charge the sphere holds. Q is going to be equal to, using this equation, rho equals Q over V. You multiply the volume of the sphere, which is going to be, I'll just write volume, times rho. This can expand into Q equals volume of a sphere, 4/3 pi r cubed times rho. Now I've solved for the charge because I know this radius, this should be capital R. I know this radius, and I was given this charge density. So now I've figured out the charge. So again, you may ask, why is that important? Well, because if I need to solve for the electric field somewhere inside this sphere that is less, that's a smaller radius than the actual sphere. So let's say I want to know my Gaussian surface is this red, and I want to know the electric field some distance little r. So let me type that out. Let me What is the electric field at point little r, which is less than big R, in this sphere with charge density rho? Now before, with Gauss's law, all we had to do was figure out how much the area was of our Gaussian surface, and then plug in the Q and the Q that they gave us if we were outside the sphere, or our Q enclosed would be 0 if we're inside. But the problem here is that since this is a uniformly charged non-conducting sphere, since this is a uniformly charged non-conducting sphere, so it's something that's not metal, maybe it's wood that's being held at some charge number. This means that my Gaussian surface inside is not containing all of the charge. It is also not containing none of the charge. It's containing some level of charge that I have to figure out. And that amount of charge is going to be some ratio of my Gaussian sphere, so little r, to my actual sphere, big R. And if I know how densely packed the charges are, I can figure out how much charge I've enclosed in my Gaussian sphere. So my next step is I'm gonna then write my Gauss's law. And then write Gauss's law. So I know to solve for the electric field at some point r, little r, I'm gonna write E dot dA equals Q enclosed over epsilon naught. This is going to be equal to, I'm going to do this integral over this entire area. So I'm going to just get the area of a circle, or area of a sphere. So 4 pi. And I'm going to concentrate on my Gaussian sphere. So I'm going to use lowercase r squared is equal to Q enclosed over epsilon naught. I still have an unknown here because I don't know how much charge I've enclosed. So I have to figure out Q enclosed. So my next step is going to be Q enclosed is equal to question mark. Now, like I said, if I take the ratio of my volumes, I will be able to figure out my Q enclosed. So I'm going to take the ratio of the volumes, and then I'm going to multiply it by this charge that I've solved for, and that will give me how much Q I've enclosed. I want it to be a smaller number, so my top side of my ratio is going to be the volume of the Gaussian sphere divided by the bottom is going to be the volume of my given sphere. And if I multiply this by Q, this will give me Q enclosed. Okay, so volume of a sphere is 4/3 pi. I'm going to use little r cubed. Divide this by the volume of my non-Gaussian surface, my regular sphere, pi big R cubed. Oftentimes students will say that you just need to do R over R. And this is a reason why it won't work, is because these R's are cubed. And R over big R is not equal to R cubed over big R cubed. So don't make this mistake. But something that will happen is that my 4/3 and my pi's will cancel, and I will get R cubed over R cubed, and then I can multiply by Q, and this will give me my Q enclosed. So now I can plug in Q enclosed into my Gauss's law equation. So I'm going to get E times 4 pi little r squared equals R cubed over big R cubed times the charge that I solved for, Q. You could plug in 4/3 pi big R cubed times rho if you wanted to. But I will just plug in Q here. And don't forget to divide also by epsilon naught. So then here I can multiply both sides by 4/3 by 4 pi r squared. So my electric field is going to be equal to, my r's are going to cancel, and I'm going to get r times q over r cubed 4 pi epsilon naught. And this, you should get an answer of this form or something similar if you are doing the electric field inside of a uniformly charged non-conducting sphere. So that's the idea of this type of Gauss's law problem. I think I will do a third video of a different shape other than a sphere. But just to talk through it real quick, for your area is going to change here. It is no longer going to be the area of a sphere. It's going to be the area of your new shape, which is probably going to be a cylinder. You would plug in your area of a cylinder here and then solve it very similarly the same. You might have to use this line charge density instead. And then there are cases where you do have to use the surface charge density too. So Gauss's law, you have to pay attention to the shape, pay attention to if it's conducting or non-conducting so that you know where the charge is. And once you know the shape of your object and where the charge, you can figure out whether or not or how much charge you are enclosing in your Gaussian surface. If you can do all three of those steps, then you will be successful with Gauss's law. All right, see you guys later. That's all I got. Hope you have a good rest of your day, and happy April Fool's Day. There's no jokes in here, but happy April Fool's Day. Uh, see ya.